Hello everyone. In this video we'll be looking at volumes of revolution. By the end of today you'll be able to tell everyone exactly why there's a factor of 1/3 in the formula for the volume of a cone, a factor of 4/3 in the formula for a sphere, and determine the precise volume of many other strange looking shapes. So to start, we're going to describe the solid shape that would result when the areas shown below are rotated one complete revolution in space about the x-axis. So we'll mark them 1, 2, 3, 4, 5, and 6. Well, we don't actually have to imagine what these shapes will look like. We can just look at them with the power of Wolfram Alpha. They are not paying me for this implicit endorsement, but I wouldn't be overly opposed if they eventually did. So here's number 1, number 2, number 3, number 4, number 5, and number 6. For whatever reason, this one always scaled to be a longer cylinder. I couldn't seem to find a way to make it a flatter disk. So the shapes that you imagined, or witnessed, are called volumes of revolution, and it is possible to determine the actual volume of the shape if the functions that bound the area is known. So let's look more closely at the area in the middle of the bottom row. A narrow rectangle that is bounded by the x-axis is drawn and shaded. The height of the rectangle is given by f at xi, and the width of the rectangle is given by delta x. If we imagine rotating the rectangle around the x-axis one complete revolution, the shape that would be produced is a disk, or a cylinder, with a radius of f at xi and a height of delta x. The volume of that cylinder can be found using the formula pi r squared times h, which is the formula for the volume of a cylinder. And we can adapt that with the values here, and our formula would become pi times f at xi squared times delta x. So now you can imagine infinitely many adjacent disks of infinitely narrow height creating the volume of the shape produced by rotating the area under f. If we add up the volume of all those disks, then we get the volume of revolution. So therefore this sum of pi times f at xi squared times delta x is equivalent to the following integral: pi times f at x squared dx. So in this first example, we need to determine the volume of the solid produced by revolving the area between y equals 2x and the x-axis, one revolution about the x-axis, from x equals 0 to x equals 3. So we can use the formula we just determined, volume equals pi times the integral from a to b of f of x squared dx. F of x in this case is 2x, so we make that substitution into this formula. The integral goes from 0 to 3, and 2x all squared would be 4x squared dx. You can bring the 4 out front of the integral sign if you like, and x squared would have come from the derivative of x cubed divided by 3. And we need to evaluate that from 0 to 3. I left out the constant of integration just now because it doesn't really matter with a definite integral. So this would be 4 pi times 27 minus 0, which works out to 36 pi units cubed. For the next example, we need to determine the volume of the solid produced by revolving the area under y equals sine x, one revolution about the x-axis, from x equals pi over 2 to x equals 5 pi over 6. So we can start with our formula v equals pi integral from a to b of f of x squared dx. In this example, we would have pi. The limits of integration would be pi over 2 to 5 pi over 6. I would sub sine x in for f of x, so I would have sine squared of x dx. And we've actually done this integral before fairly recently. In order to do this integral, we need to use the following identity. Sine squared theta equals 1/2 1 minus cos of 2 theta. So our integral would become pi times 1/2 integral of dx from pi over 2 to 5 pi over 6 minus 1/2 integral of cos 2x dx from pi over 2 to 5 pi over 6. I guess we could pull these factors of 1/2 out front next to the pi. So next we would have pi over 2. The integral of 1 is just x, and we need to evaluate that from pi over 2 to 5 pi over 6. I've again excluded the constant of integration because it's not really important with a definite integral. In order to do this second integral, it would be helpful to substitute u equals 2x. So So that means du equals 2 dx, and du over 2 equals dx. We can change our limits of integration as well. So when x equals 5 pi over 6, u equals 5 pi over 3. And when x equals pi over 2, u equals pi. So the integral of cos 2x dx can be rewritten as cos of u with a 1/2 out front. And cos would have come from a derivative of sine. So we would write this integral here as negative 1/2 sine of u evaluated from pi to 5 pi over 3. If you're wondering whether or not I neglected to deal with this factor of 1/2, it actually came from this substitution, and the other factor of 1/2 has already been dealt with. We can now substitute our limits of integration. So next we would have pi over 2, 5 pi over 6 minus 3 pi over 6. That's equivalent to pi over 2. And then we would have negative 1/2. Sine at 5 pi over 3 is negative root 3 over 2. And sine at pi is 0. Next we would have pi over 2. 5 pi over 6 minus 3 pi over 6 is equivalent to 2 pi over 6. And this whole thing simplifies to root 3 over 4. So finally, I guess we can distribute this pi over 2 into each of these terms, and we would end up with pi squared divided by 6 plus root 3 pi over 8 units cubed. In example number 3, we're looking to determine the volume of the solid produced by revolving the area enclosed by 4 root x and 2x about the x-axis. So if you rotated this shaded shape around the x-axis, you would end up with a tall round bowl on the outside with a sharp rim and a cone-shaped interior. Again, we can use our formula v equals pi integral of f of x squared dx from a to b, but this time we need to determine two volumes. First, we can determine the volume produced by this curve when it's rotated about the x-axis, and subtract off the volume produced by this line when it's rotated about the x-axis. So the volume of this shaded shape will be given by the outside volume, given by pi integral of 4 root x squared dx from 0 to 4, minus the inside volume, which is pi integral of 2x squared dx from 0 to 4. And this would give us 16 pi integral of x dx from 0 to 4 minus 4 pi integral of x squared dx, again from 0 to 4. This derivative would have come from an x squared over 2. So we have 16 pi x squared over 2. We need to evaluate that from 0 to 4. I've left out the constant of integration. It's a bit sloppy, but it saves me a little bit of writing. An x squared would have come from an x cubed divided by 3. So for the second term, I have negative 4 pi x cubed divided by 3, evaluated from 0 to 4. So now if I sub in my limits of integration, I have 16 pi, 8 minus 0, minus 4 pi, 64 over 3. This first term goes to 128 pi, and the second term goes to negative 256 pi over 3. I can add these terms together, turn this number into something over 3, and I get a final answer of 128 pi over 3 units cubed. In example number 4, we need to determine the volume of the solid produced by revolving the area enclosed by 2 to the x-axis, root x minus 1 revolution about the x-axis from 0 to 2. So you can imagine this shaded shape, when rotated about the x-axis, would produce a wide lampshade looking thing with a flat bottom and a paraboloid scooped out from the center. It would be an awkward container to drink from. So again, we can start with our formula, v equals pi integral of f of x squared dx from a to b. We can start by determining the volume produced by rotating this curve around the x-axis, and subtract off the volume produced by rotating this curve around the x-axis. So the volume of the shaded bit rotated around the x-axis would be given by the following expression. We would have pi integral of 2 to the x squared dx from 0 to 2 minus pi integral of x minus 1 to the 1/2 squared dx from 1 to 2. So we can simplify this a little bit. We would have pi integral of 2 to the 2x dx from 0 to 2 minus pi integral of x minus 1 dx from 1 to 2. This second integral should be fairly straightforward, and fortunately we have something for the first integral as well. On our formula sheet we have a to the u du equals a to the u divided by ln of a plus c. We're going to let u equal 2x, so that means du equals 2 dx. We can adjust our limits of integration as well. When x equals 0, u equals 0, and when x equals 2, u equals 4. So this first integral would become pi integral of 2 to the u du. Now dx needs to be replaced with 1/2 du, so I need to bring that into play. And my limits of integration are from 0 to 4. The second integral would stay the same, and now we can carry on integrating both of these terms. For the first integral, we would have pi over 2, 2 to the u divided by ln of 2 from 0 to 4. And for the second integral, we would have negative pi x squared divided by 2 minus x evaluated from 1 to 2. Putting in our limits of integration, we would have pi over 2 ln of 2 times 16 minus 1, because 2 to the 0 is 1. Then we subtract pi, 2 minus 2, which goes to 0, minus 1/2 minus 1. Next we would get 15 pi divided by 2 ln of 2 minus pi times 1/2. We can clean this up a little bit further using one of our log laws. So we would have 15 pi over ln of 4 minus pi over 2. So that's it for me for today. You can do this question, which might be one of your crowning achievements for the day. Just remember that the formula for the area of a circle is given by x squared plus y squared equals r squared. Adios.